Welcome to a session for all problems. Okay, so I went into many books and I actually picked up Kleppner and Kolenkow's book to focus on. Today we are going to do a whole bunch of problems. Okay, so if you're following along my series on introductory physics, you can actually do these problems on yourself and then come check with later. I'll just put all of them in one video, okay, so that it will be in one place for you to follow. Okay, so here is the first problem. So always when you look at the problem, actually just read the words, you can get pretty easily confused. So you draw a picture. So these are position vectors. So you need an origin. And let's see, this is a vector R1. So this is some point P1. So this is location of point P1 or position of point P1. It's not given, but I'm drawing it like that. And this is some other vector R2 to point P2. So and these two, the distance between them is given to be r. According to this, the distance is denoted as r. And we're supposed to find, there is a point here which is a distance xr. X maybe, you should say x. I'm going to draw so that xr is between P1 and P2 distance. It can be x can be bigger than that. It can be along that line. If x is greater than 1, so that will be x greater than 1, and it will be between this and this if x is between 0 and 1. So I'm going to just, for the sake of drawing, I'm going to draw like that. So the vector A that we want is this vector. This vector is vector A. So you can see that if I think of this as a vector here, then I will be able to say, so let's call it vector V. So A will simply be R1 plus vector V. So how do I get vector V? What's given is magnitude is equal to x times r, and the direction is between P1 to P2. So this direction, you can, if you say P1 to P2 is this big vector here, let's call it r vector. So the magnitude is r vector. You can see the r vector is simply going to be if you IR, it will be r plus r1. So this plus this must be equal to r2. So r is simply r2 minus r1, right? So r is r2 minus r1. And so the direction, what's the direction of this vector? It will be in the unit vector. So direction of r is a direction in which the V is. So what's the direction of r? You say, I'm going to use unit vector to denote direction, and that will be r2 minus r1 over r2 minus r1. And this is simply same as this. Putting a minus sign here doesn't change that. So that's the vector V just turns out to be this, the magnitude. And let's call this unit vector. So xr times unit vector. And I put this in there. So that's going to be xr times v2 minus v1 over r. X cancel out. And so the A vector is simply r1 plus x times r2 minus r1 or you can combine the r1s together. It's going to be 1 minus x along r1 plus x times r2. So that's going to be the answer. So this actually is a very important problem. A lot of vector algebra later on, when you're going to do in physics, make use of this very simple algebra. Okay, so welcome to the second problem. This is actually a very good problem also. Not easy to solve, but again, if you think in terms of vectors, you'll be able to solve it. So try to solve this on your own, and you can come back to my solution. You can pause it and come look at my solution a little bit later. Okay, so here's the solution. So first I'll look at it. This part is, so we have a vector. This part is another vector parallel to n hat, right? Because there's some number times n hat. If this is positive, it's in the direction of n hat. If it's negative, it's the opposite direction. So this is, and this vector, we'll have to see that this is must be perpendicular to n hat. Okay, so if you think about vector A and n hat will make some plane. So here's the vector A, and so this is n hat, and so n hat magnitude is 1, and A vector magnitude is some A. This is 1. Okay, and let direct angle between them be theta. It's like that. So this is, you can see that this is forming a plane, we already know, in which these two vectors lie. So if I look at it, if I project on this, so this part is A dot n hat, which is A n hat cosine theta, which is A cosine theta. Now this part, if you look at that part is A sine theta. But if I had to do A cross n hat, its magnitude will be A n hat sine theta. So I can see, if I knew what is the vector in that direction, then I could just write down, say there's a unit vector in that direction, then I could just add this up, right? I could add vector this and this to get A. But actually it's hard to get a vector like that. So because when I do A cross n hat, this has to be perpendicular to this plane, and that, let's write down, so this is A cross n hat vector. Now this direction is the direction in which is perpendicular to both n hat. So this is perpendicular to both this direction, this direction. So this is actually perpendicular to in that direction, and this. And so you can say, let's call this direction u hat. U hat is perpendicular to A cross n hat and n hat, to both. So if I do we do the right hand rule, then u hat is in direction of A cross n hat cross n hat. So now if you look at this, what's the magnitude of this will be? A cross n hat cross n hat, its magnitude will be magnitude of A cross n hat times n hat, and we already know these A cross n hat and this guy 90 degrees, so the angle between this vector and this vector is 90 degrees, sine 90 degrees. So that, and this one we already figured out, magnitude is A sine theta, and this is 1 and this is 1, so this whole thing is times 1 equals to A sine theta. So we notice that not only this thing is in the direction we want, but also has the magnitude we want. So let's call it some point O, and let's call it point P, a point Q, and so vector A, which is O to Q, is equal to O to P vector plus P to Q vector, and O to P vector will be magnitude times the direction unit vector. So A dot n hat, and this is we already figured out by doing that. The direction is u hat and magnitude is A sine theta. So this shows that this must be equal to, so PQ is equal to this whole thing, and OP equal to this thing, and OP and P vector wise added together gives him L. So that's how, in a way, a very simple problem, but you have to go like one step further. You take two cross products to get back to the direction you want. Okay. All right, let's do the next problem. Okay, so welcome to another problem. And so this problem is a projectile motion problem. So some projectile is going, and at different levels it goes up and then it's going to come back on the same level. So you can think of this as like an x-axis. This is like horizontal. So at some point it goes up, say at height A, marked A, and then goes to A1, and then goes to B1, and then comes back to this is same height B, B2, and comes to A2, and then it keeps falling. So this is a free fall. This is a free fall time. Between time it was at the same height at two different places, the time difference is TA and time difference is T2, TB here. And so if you set up the problem, from there you're supposed to deduce that this will be the answer. That's a very good problem. I can just give you a hint that you can assume that this is, you can say this is t equal to 0 situation, and this is theta, and this is start with v0 initial speed, and then you will be able to set this up, and then you can solve this problem. Try solving this problem and you can come back to it. You might get lost a little bit, then you can try a couple of times. If you don't get lost, that's great. All right, so you can pause and then come back. Okay, so I'll give you a chance to pause. All right, so let's do it out. We can say from here to here, I'm gonna call it just some couple of things you can say. If you go from same height to same height, so A1, let's look at A1 to A2, this whole deal, okay, A2, so the y final minus y initial, this is the y final, and this is the y initial. So this the same is equal to 0, so delta y equal to 0, and v0y is v0 sine theta from here. So you have a v0 theta, and this is x, and this is y. So we can call this x and this is y. Sine theta, and ay equals to minus g, because positive y is pointing this way, g is pointing that way. And the time t final minus t initial, which is usually t in the formula, is denoted as ta here. So from here you can already say that 0 equals, I'm going to use delta y equal to v0 yt plus half ay t squared. So we're going to use this formula. So 0 v0y is v0 sine theta, and ta plus half ay ta squared. So now you can take ta common, and this is minus g. So you can see that ta is not 0 because it's coming back later. Ta is not 0. So ta is, you can do it over here, that's going to be 2v0 sine theta over g. So wherever I see this expression, I can call it ta. Okay, now let's see how we're going to handle b1 to b2. So rather than do b1 to b2, because then I'll need initial velocity there, which we can work out. That's another way to do it. But I will much rather prefer to do a1 to b1 or b2. So I'm going to start with a1 because I already introduced the initial velocity there. a1 to b1 b2. I'm going to capture both of them by just looking at y. If we look at y motion only, let's see what we get. So that's going to be y final minus y initial is going to be h for this delta y, and v0y will be the same because I'm starting this that place, which will be v0 sine theta, and this ay will be the same, it's going to minus g. The t, let's call this time here is t1, then time here will be t1 plus tb. So so that's going to be some time, all right? And you're going to capture those things right by just saying a t. So I'm going to have two values for t. So this just going to use the same symbol for t. And when we solve, I'm going to get two answers. You will see. So one of them will be t1, another will be t2, t1 plus tb. Okay. So I'm going to set the equation like this. So that's going to be h. This quadratic you can get. So h equals to v0 sine theta times some unknown t, which will have two answers because at that height there are two places can be in time, minus half gt squared. So now this is quadratic. Over here it was quadratic also, but one of them was not the answer. But one of the answer for t equal to at this instant over here rather than a2. So this one you can see that v0 sine theta, let's make sure that we can multiply by 2h over g and 2 over g, and can get rid of that. This thing here is going to be ta minus t square, and let's try to solve this quadratic equation. Let me erase something. Okay, it can now be solved as t. There should be two answers to that. 1 over 2 dA plus minus square root of dA square minus 8h over g. So we were going to get a T1 and T1 plus. So you can see from here that T1 should be half dA minus square root of dA square minus 8h over g, and T1 plus TB should be same thing with a plus here, like that, right? So if I subtract out, I'm going to get a TB equals to half plus half must be square root of dA square minus 8h over g. Now if you simplify it, retransform it, you're going to get that answer. So there are other ways of doing it, but I find this is a more direct way. I'm just looking at why motion is sufficient to solve this problem. Welcome to another problem. So this is a really very standard problem in which there are two motions of two objects that are somehow linked, and we have to set up the equation so that we can link them properly. Okay, so always it's kind of helpful to draw pictures, right? So here is a elevator with maybe a little hole down here, and elevator is climbing up with some constant speed v not given. So this is going up at constant v. So at time t, when t equals to t1, a ball is dropped from here. So ball now falls, is going to hit the ground, and t now will be t1 plus t2. So this time it takes is t2, and this time in the elevator is t1, and this is falling this way with a g, and this height is h. That's the height we need to know. Now if v was given, then clearly v is equal to h over t1. That will solve h equals to v times t1, right? But v is not given. So in this equation is correct, but there are two unknowns here. So we can of course use v and later on replace v with h over t1 in our equations. So that's the link. The link is this is the elevator's motion. Elevator will give me this equation, and then I have to look at the marble equation. So marble, and you have to be careful. Maybe you can pause it here and try to solve it by yourself. There is a little subtlety into analyzing the situation. I don't want to take it away from you. You can pause it and think about it a little bit, and then come back to this video. Okay, so the main problem is that when you let go of this marble is, this elevator is still going at constant v. That means the marble is going constant v. So the initial velocity of the marble is v. And if you take this is the y-axis, positive y-axis, then v0y will be v. And ay will be minus g because it's pointed down, and up axis that way. And y final is here, and y initial is here. Y final minus y initial will be minus h. and delta t will be t2 because it took t2 amount of time to get from here to there. So using this, the marble equation just look like minus h equals to v delta t minus half g delta t square, which makes it minus h. For v, I can use h over t1 and delta t is t2 minus half g dt square. So now I can bring this side, bring this side. So h 1 plus t2 over t1 equals half g t2 square. And so the h is, now I can solve it. Half g t2 square 1 plus t2 over t1. So you can just multiply by t1 on both sides, and the answer can be written as half g t1 t2 square over t1 plus t2. So that's the answer. I hope I didn't make any mistakes in the algebra here, but this is a pretty good problem. It really, that's the catch. Take care. I'm going to move on to the next problem. Welcome to a problem in relative velocity. This problem and the next problem actually makes use of relative velocity concept. So this problem actually kind of defines what relative velocity means, right? So relative velocity means the velocity with respect to a specified coordinate system. So in this picture, for instance, will be both A and B are moving, but I want to know the velocity of A with respect to B, not respect to, say, point O or something like that, not with the origin, but with respect to this object. Okay. So if I were to put a coordinate system here, what will be the velocity of A with respect to the coordinate system of B? All right. Given the velocity of A and velocity of B with respect to O. So when we say the velocity of A, we say velocity with respect to the observer. So this pink thing is, this is like an observer. So that with respect to the observer, that velocity is just regular velocity. But when we say velocity with respect to somebody else, we're talking about were you able to make the other thing as an observer, then what will the velocity with respect to that observer? It plays an important role in physics, relative velocity. So it's a good idea to get a hang of it, okay? So the first problem is not to do with this picture, but another, this is a general problem. This is general. So I will say, let's look at in this way. So we have a frame A and we have a frame B, and we are looking at something, both of them looking at this. Okay, so it's saying what is the velocity, say a point is observed to have velocity VA. So when we look at with respect to this, its velocity is VA, then what's the velocity with respect to B? Displacement like that. B is displaced like that. So this is R, which may depend on time. So this is right now, say at some time t, this is the situation. And this vector we call RA vector. And from here is RB vector. All right, so let me just clean some place and try to get some space. So we can right here in this triangle, we can say that RA is RB plus r, just the vector relation. And each one of them is a function of time, right? So the velocity is just take a time derivative of this. So if I if I have RA is RB, RB is the position with respect of, so the time derivative of that will be the velocity VB. So plus R. So each time derivative is what tells me the velocity with respect to B. So let's do the RB equals to RA minus R. Time derivative gives me drB dt equals dra dt minus dr dt. This is what we are calling velocity with respect to A, and this velocity with B. So it's very easy to see that velocity with respect to B. This is what we want to know. Is A minus how fast B is moving with respect to A. dr. So sometimes instead of writing RAR, we can write R of B with respect to A, R of B with respect to A, R of B with respect to A. Sometimes when you have two different frames, you want to be more specific and more clear about what the symbols will mean. You attach more subscripts to them. Okay. So let's do the B using these ideas. Okay, so let's we have a situation where it says initially they were here and in time t they moved over here. So this angle is omega t. So if I call this RA, so you have a RA vector. So RA vector is simply going to be x of A and y of A. That will be these components. So x of A is, looking at this is the angle, and this is little r, which is constant because in a circle. So x of A, if this is theta, then it's going to be sine. So it's going to be r sine theta, and theta is omega t. Omega t is the amount of angle that discovered while moving in a circle with angular velocity omega for time t. And the other one is r cosine omega t, and both are positive. This is positive, and this projection is also positive. When I look at R at B, XB, YB, its projection will be, it also covers the same amount because the omega is same, but XB will be negative while YB will be positive. Minus R sine omega t, R cosine omega t. And we want velocity of A with respect to B. So we want the velocity of this thing, and so with respect to this thing, right? So we will say, where is this thing? Where is this thing when I'm at B? So we want that vector. How is that vector changing in time? So let's call it a script R vector. So in my triangles, a script R vector is this way, RB is that way, and RA is that way. So look at the triangle relationship. So we want R, so this plus this equal to that. So RB plus R equals to RA. So R is RA minus RB. And if you put this in there, its components will be 2 times r sine omega t and 0. Clearly some pointed towards the x-axis in our diagram. So if I say dr dt will be just 2 omega r cosine omega t and along I hat. So that's how simple it is. It's actually a lot of the relative velocity problems can be solved if you can construct this triangle of vectors correctly. Okay, so I'm going to stop my solution now, and I'll move to another problem that uses relative velocity. Welcome to another problem. We have this is also a standard problem actually, and kind of stumps people if you don't use a relative motion, then you can actually get lost in the problem quite a bit. So this situation of the tire moving with respect to this frame, the observer's frame, so we can just call this observer's frame. And you can see if you were at another frame called this center of the tire frame, you won't be moving, but with respect to you, the spable will be just going around in this circle. So you can see that this is let's call it a C frame. Let's call it point C over here. Then we can have let's see, this one vector. We want to know this vector. Let's call this, we want that. That's what it's saying. Find principal velocity as a function of time, and it's asking it to give in the frame O. Then with respect to this frame O, C is very easy, you know. So the velocity of C, and let's call this this is R vector, and you can see another vector from here to here. We can that vector, let's call this C vector. I'm just going to R vector. Maybe call this guy C vector, where the C is located. All right. So in this diagram, if you could figure out these guys, we could figure out this guy. So the R will be this plus R will be C plus R, but we need to figure these guys out. Well, C is, say this is the x-axis, this is the y-axis, so this is I hat, and this is j hat. So this distance remains the same, so C is very easy to get. Its x-coordinate is how far it has gone, is when pebble was touching over here, so this much is the same as that much distance, and so that's just v times t. That's how far it has gone in the x-axis. In the y-axis, it's constant, whatever the radius of the tire is. The radius of the tire is not given. Let's call it r equals to radius of the tire. Or if you want to write down in terms of I hat and j hat, will be like that in terms of the vectors, right? And what is little r? Little r is in this coordinate system. If I know this angle, I'll be pretty right. It will be so. What is the angle? The arc distance is the same as that distance. Arc distance is BT, radius is R, we pick the R. So the angular velocity is, Vt over R. That's the angle. The angle, not angular velocity. The angle will be, theta will be Vt over R. And so if I know this, so that's the theta. So in this coordinate system, also this is I hat and this is j hat. In that coordinate system, it's x is we can actually do x and y so that it's much easier. Everything is positive. So I like to do it so that this is with respect to which the angle is being measured, because it's rotating that way. So let's call this I hat prime, and let's call that guy, this direction, j hat prime. So this is this is its y prime and this is x prime. Just pick a more convenient one. You can see that I hat prime is minus j hat and j hat prime is minus I hat, for the sake. So if you win that, it's very easy to get R cosine theta for the x-axis coordinate and R sine theta for the y-coordinate. But these guys using I hat prime, j hat prime. So let's write that down in the prime coordinates. So I cosine theta is Vt over R. Vt over R. Okay. I hat prime plus R sine Vt over R j hat prime. Now this is just minus j hat and this one's minus I hat. So I get minus R sine Vt over R I hat minus R cosine Vt over R j hat. So now we're done, and actually all I have to do is do derivatives, right? So I got R of t is this minus that, Vt minus R sine Vt over R I hat. So written down in the same I hat and j hat, and the other thing is R minus R cosine Vt over R j hat. Well, what will be the velocity? Velocity will be just take a derivative of this. So this derivative will give me v, and this derivative will give me from here also minus v, but cosine Vt over R will cancel out, right? I hat. This will go to 0 and this will come up plus v sine Vt over R j hat. What will be the acceleration? Acceleration will be take time derivative of this guy. It's going to be v square over R sine Vt over R I hat plus v square over R cosine Vt over R j hat. If you want to get a magnitude, so magnitude of acceleration will be just square of this plus square of that, and sine cosine, it will be a constant actually, v square over R. If you work it out, that's the magnitude. But magnitude of the velocity will have some terms. For magnitude of the velocity, we'll have to work a little bit more. So you'll have square root v minus v cosine vt over r square plus v square sine square vt over r. And you can see this square of this will combine with that, and so you can write v square plus v square, so it's going to be 2v square minus 2v square cosine vt over r. And you can take out you can simplify further, but this is okay. You can simplify further and use double angle formula and things like that to simplify more. But this may be enough. Direction will be, of course, you can do arctangent and things like that. But you can leave it as it is. Okay, so I think when I'm done with the problem that I picked from Kleppner and Kolenkow. There are other problems also in that book. They're all very, very good problems for you to try. Okay? All right. Take care. Bye.